We've talked a little bit about the lungs and the tissue and how there's a kind of an interesting relationship between the two where they're trying to send little molecules back and forth. The lungs are trying to send, of course, oxygen out to the tissues, right? And the tissues are trying to figure out a way to efficiently send back carbon dioxide. So these are the kind of core things that are going on between the two. And remember, in terms of getting oxygen across, there are two major ways we said. The first one, kind of the easy one, is just dissolved oxygen in the blood itself. But that's not the major way. The major way is when oxygen actually binds hemoglobin. In fact, we call that HbO2, and the name of that molecule is oxyhemoglobin. So this is kind of how the majority of the oxygen is going to get delivered to the tissues. And on the other side, coming back from the tissue to the lungs, you've got dissolved carbon dioxide. A little bit of carbon dioxide actually literally comes just right in the plasma. But that's not the majority of how carbon dioxide gets back. The more effective ways of getting carbon dioxide back, remember we have this protonated hemoglobin. And actually, remember when I say there's a proton on the hemoglobin, there's got to be some bicarb floating around in the plasma. And the reason that works is because when they get back to the lungs, the proton, that bicarb, actually kind of meet up again and they form CO2 and water. And this happens because there's an enzyme called carbonic anhydrase inside of the red blood cells. So this is where the carbon dioxide actually gets back. And of course, there's a third way. Remember, there's also some hemoglobin that actually binds directly to carbon dioxide, and in the process, it forms a little proton as well, and that proton can go do this business, right? It can bind to a hemoglobin as well. So there's a little interplay there, but the important ones I want you to really kind of focus in on are the fact that hemoglobin can bind to oxygen, and also on this side, that hemoglobin actually can bind to protons. Now, the fun part about all this is that there's a little competition, right? A little game going on here. Because you've got, on the one side, you've got hemoglobin binding oxygen. And let me draw it twice. And let's say this top one interacts with a proton. Well, that proton's going to want to snatch away the hemoglobin. And so there's a little competition for hemoglobin. And here the oxygen kind of gets left out in the cold. And the carbon dioxide does kind of the same thing we said. Now we have little hemoglobin bound to carbon dioxide, and it makes a proton in the process. But again, it leaves oxygen out in the cold. So depending on whether you have a lot of oxygen around, if that's the kind of key thing going on, or whether you have a lot of these kinds of products, the proton or the carbon dioxide, depending on which one you have more of floating around in the tissue in the cell, will determine which way that reaction goes. So keeping this concept in mind, then I could actually step back and say, well, I think that oxygen is affected by carbon dioxide and protons. I could say, well, these two, carbon dioxide and protons, are actually affecting the, let's say, the affinity or the willingness of hemoglobin to bind, of hemoglobin for oxygen, right? That's one kind of statement you could make by looking at that kind of competition. And another person come along and they say, well, I think oxygen actually is affecting, depending on which perspective you take. You could say oxygen is affecting maybe the affinity of hemoglobin for the carbon dioxide and proton, of hemoglobin for CO2 and protons. So you could say it from either perspective. And what I want to point out is that actually, in a sense, both of these are true. And a lot of times we think, well, maybe it's just saying the same thing twice. But actually, these are two separate effects, and they have two separate names. So the first one, talking about carbon dioxide and protons, their effect is called the Bohr effect. So you might see that word, or this description. This is the Bohr effect. And the other one, kind of looking at it from the other perspective, looking at it from oxygen's perspective, this would be the Haldane effect. That's just the name of it, Haldane effect. So what is the Bohr effect and the Haldane effect, other than simply saying that the things compete for hemoglobin? Well, let me actually bring up a little bit of the canvas, and let's see if I can't diagram this out, because sometimes I think a little diagram would really go a long way in explaining these things. So let's see if I can do that. Let's use a little graph and see if we can illustrate the Bohr effect on this graph. So this is the partial pressure of oxygen, how much is dissolved in the plasma. And this is oxygen content, which is to say how much total oxygen is there in the blood. And this, of course, takes into account mostly the amount of oxygen that's bound to hemoglobin. So as I slowly increase the partial pressure of oxygen, see how initially not too much is going to be binding to the hemoglobin. But eventually, as a few of the molecules bind, you get cooperativity. And so then slowly, the slope starts to rise and becomes more steep. And this is all because of cooperativity. Oxygen likes to bind where other oxygens have already bound. And then it's going to kind of level off. And the leveling off is because hemoglobin is starting to get saturated. So there aren't too many extra spots available. So you need lots and lots of oxygen dissolved in the plasma to be able to seek out and find those extra remaining spots on hemoglobin. So let's say we choose two spots. One spot, let's say, is a high amount of oxygen dissolved in the blood. And this, let's say, is a low amount of oxygen dissolved in the blood. I'm just kind of choosing them arbitrarily. Don't worry about the units. And if you were to think of where in the body would be a high location, that could be something like the lungs, where you have a lot of oxygen dissolved in blood. And low would be, let's say, the thigh muscle, where there's a lot of CO2, but not so much oxygen dissolved in the blood. So this could be two parts of our body. And you can see that now if I want to figure out, looking at this curve, how much oxygen is being delivered to the thigh, then that's actually pretty easy. I could just say, well, how much oxygen was there in the lungs or in the blood vessels that were leaving the lungs? And there's this much oxygen in the blood vessels leaving the lungs. And there's this much oxygen in the blood vessels leaving the thigh. So the difference, whatever oxygen is between these 2 points, that's the amount of oxygen that got delivered. So if you want to figure out how much oxygen got delivered to any tissue, you can simply subtract these two values. So that's the oxygen delivery. But looking at this, you can see a kind of an interesting point, which is that if you wanted to increase the oxygen delivery, let's say you wanted, for some reason, to increase it, become more efficient, then really the only way to do that is to have the thigh kind of become more hypoxic. As you move to the left on here, that's really becoming hypoxic or having less oxygen. So if you become more hypoxic, then yes, you'll have maybe a lower point here, maybe a point like this, and that would mean a larger oxygen delivery. But that's not ideal. You don't want your thighs to become hypoxic. That could start aching and hurting. So is there another way to have a large oxygen delivery without having any hypoxic tissue or tissue that has a low amount of oxygen in it? And this is where the Bohr effect comes into play. So remember, the Bohr effect said that CO2 and protons affect the hemoglobin's affinity for oxygen. So let's think of a situation. I'll do it in green. And in this situation, where you have a lot of carbon dioxide and protons, the Bohr effect tells us that it's going to be harder for oxygen to bind hemoglobin. So if I was to sketch out another curve, initially, it's going to be even less impressive with less oxygen bound to hemoglobin. And eventually, once the concentration of oxygen rises enough, it will start going up, and it does bind hemoglobin eventually. So it's not like it'll never bind hemoglobin in the presence of carbon dioxide and protons, but it takes longer. And so the entire curve looks shifted over. These conditions of kind of high CO2 and high protons, that's not really relevant to the lungs. The lungs are thinking, well, for us, who cares? We don't really have these conditions. But for the thigh, it is relevant because the thigh has a lot of CO2 and the thigh has a lot of protons. Again, remember, high protons means low pH, so you can think of it either way. So in the thigh, you're going to get then a different point, right? It's going to be on the green curve, not the blue curve. So we can draw it at the same O2 level, actually being down here. So what is the O2 content in the blood that's leaving the thigh? Well, then to do it properly, I would say, well, it would be over here. This is the actual amount. And so O2 delivery is actually much more impressive. Look at that. So O2 delivery is increased because of the Bohr effect. And if you want to know exactly how much it's increased, I could even show you. I could say, well, this amount from here down to here. Literally the vertical distance between the green and the blue lines. So this is the extra oxygen delivered because of the Bohr effect. So this is how the Bohr effect is so important at actually helping us deliver oxygen to our tissues. So let's do the same thing now, but for the Haldane effect. And to do this, we actually have to switch things around. So our units and our axes are going to be different. So we're going to have the amount of carbon dioxide there. And here we'll do carbon dioxide content in the blood. So let's think through this kind of carefully. Let's first start out with increasing the amount of carbon dioxide slowly but surely and see how the content goes up. And here, as you increase the amount of carbon dioxide, the content just kind of goes up as a straight line. And the reason it doesn't take that S shape that we had with the oxygen is that there's no cooperativity in binding the hemoglobin. It just kind of goes up straight. So that's easy enough. Now let's take 2 points like we did before. Let's take a point, let's say up here, this will be a high amount of CO2 in the blood, and this will be a low amount of CO2 in the blood. So you'd have a low amount, let's say right here, in what part of the tissue? Well, low CO2, that sounds like the lungs, because there's not too much CO2 there. But high CO2, it probably is the thighs, because the thighs are like little CO2 factories, right? So the thigh has a high amount, and the lungs have a low amount. So if I want to look at the amount of CO2 delivered, we do it the same way. We say, okay, well, the thighs had a high amount. This is the amount of CO2 in the blood, remember? And this is the amount of CO2 in the blood when it gets to the lungs. So the amount of CO2 that was delivered from the thigh to the lungs is the difference. And so this is how much CO2 delivery we're actually getting. So just like we had O2 delivery, we have this much CO2 delivery. Now read over the Haldane effect, and let's see if we can actually sketch out another line. In the presence of high oxygen, what's going to happen? Well, if there's a lot of oxygen around, then it's going to change the affinity of hemoglobin for carbon dioxide and protons. So it's going to allow less binding of protons and carbon dioxide directly to the hemoglobin, and that means that you're going to have less CO2 content for any given amount of dissolved CO2 in the blood. So the line still is a straight line, but it's actually, you notice it's kind of sloped downwards. So where is this relevant? Where do you have a lot of oxygen? Well, it's not really relevant for the thighs because the thighs don't have a lot of oxygen, but it is relevant for the lungs. It is very relevant there. So now you can actually say, well, let's see what happens. Now that you have high O2, how much CO2 delivery are you getting? And then you can already kind of see it. It's going to be more, right? Because now you've got this much. You've got going all the way over here. So this is the new amount of CO2 delivery, and it's gone up. And in fact, you can even show exactly how much it's gone up by simply taking this difference. So this difference right here between the two, this is the Haldane effect. This is the kind of visual way that you can actually see the Haldane effect. So the Bohr effect and the Haldane effect, these are two important kind of strategies our body has for increasing the amount of O2 delivery and CO2 delivery going back and forth between the lungs and the tissues.